series of forensic science lecture. Today we are going to discuss about the infrared spectroscopy. When we talk about the infrared spectroscopy, it is one of the most versatile technique which is being used in the forensic science. So the best part of this infrared spectroscopy is that we can use solid, liquid, gas, all three kinds of sample for our analysis. So when we are using IR spectroscopy for analysis, depending upon what kind of sample we have, whether it is in solid form, liquid form or gaseous form, we can use it depending upon the sample we have encountered from the crime scene. So we categorize the sample into three parts: solid, liquid, gases, and their preparation is different depending upon the sample. If we encounter the powdered sample from the crime scene, the preparation will be through alkali halide method or maybe using Nujol. If we have encountered the liquid sample, that can be depending upon the concentration of the sample, we can use an IR transparent window cells and we can analyze using that. And for the gases, we have specialized IR transparent chambers in which the gases are being put in, where the chambers they are spacious and we can directly inject the gases and they are airtight chambers so that the sample does not eject out. So let us talk about the preparation of the samples for the IR spectroscopy. Since almost all substances they absorb IR radiation at some wavelength, so the solvents must be carefully chosen for the wavelength region and the sample of interest. This is the one important thing which we have to keep in mind, that most of the substances they absorb IR radiation. So the choosing of the sample solution for making the sample preparation should be done in a particular solvent which does not absorb IR radiation. For example, one of the common example is the KBr, potassium bromide, which is transparent to IR wavelengths, which we mostly use for the analysis. For the gas sample, as I spoke, that it consists of a cylinder of glass or sometimes a metal. The cell is closed at both ends with appropriate window materials. This appropriate window materials, when we are talking about the NaCl and KBr, they are IR transparent windows and they are equipped with valves or stopcocks for the introduction of the sample. So whenever any gaseous sample goes into that chamber, the sample should be preserved in that. We have also the long path length cells more than 10 centimeter, which is used to study dilute or few molecules or such samples which are weakly absorbing samples. So the preparation of the gas samples is quite easy. They can be directly ejected into a cylinder of glass or a metal container. Now talking about the liquid samples. So this multipass cells are there through which we can use more compact and efficient instead of long path length cells. This multipass cells, these are basically an advantage over the normal pass cells, so that the sample can go through various passes before exiting the cell. In such cases, the effective path length is greater than 10 meter, whereas when we talk about the other cells, their effective path length is greater than only 10 centimeter. So this is a very more compact and efficient ways when we are also talking about the preparation of samples for the gases. So to resolve the rotational structure of the samples, the cells must be capable of being evacuated to measure the spectrum at reduced pressure. So this is for the qualitative analysis, but further we have to identify or we have to quantitatively determine the light molecules. The cell is pressurized to broaden the rotational structure and we can go for simpler measurements. When we have any liquid samples from the crime scene, we can use directly pure or solute in transparent solvent. We never use water to make samples, liquid samples in the IR spectroscopy, because it hinders whenever the IR radiations are being passed through it. The sample which is most often used in the form of liquid films, or we can say the sample is sandwiched between two NaCl plates. Now question is, why only NaCl? Because NaCl is IR transparent. As I said, it is one of the alkali halide like KBr. They are IR transparent and they does not interfere, they do not absorb IR radiations, so that we get a free analysis of the sample which we are taking. For the liquid sample, there could be an adjustable path length 0.015 to 1 mm. So, we can use a Teflon spacer for adjusting the path lengths. So, the question is, why we are taking care of the path lengths? Because as we said, IR spectroscopy are both qualitative as well as quantitative analysis. As we have studied in the UV visible spectroscopy, the Beer-Lambert's law, absorption is equal to epsilon Cl, where we can get to the absorption, what is the quantity through the concentration and the path travelled by the light. So, using that path length we know, if we knew, then we can quantitatively determine the sample, the concentration of the samples present there, which we are analyzing using IR spectroscopy. For the solid samples, we use moles, nodule or alkali halide discs with the KBr. So, what happens there? When we are taking the KBr palette, we will take a mixture. For example, we have a powdered sample, we will make a palette. How we are making a palette? We have a pressurized machine wherever we will put the mixture as 10:1 ratio, where 10 is the KBr and 1 is our sample. So, 10 is the 1 ratio, we will make a palette with a high pressurized machine. It is similar looking to one of the medicines, we can say, like a round palette, and that can be directly analyzed using any kind of IR spectroscopy. Moles is basically an oil emulsion where we have usual oil, where thin film of oil is there, through which we can make a paste, and that can be used for the analysis of the sample. So, how to make alkali halide discs? A milligram or less of the fine ground sample is mixed with about 100 mg of KBr powder in a mortar or ball mill, and the mixture is in a die to form a transparent disc. So, if the disc is opaque, then it will not be IR transparent. We have to make our pellet to be almost transparent. For moles, we are grinding a few milligrams of the powdered sample with a mortar or any pulverizing equipment. Nujol, which we are saying, is a kind of a mineral oil which is added to form a smooth paste, and this IR of the paste can be obtained as the liquid sample. So, these are the two main different types of sample preparation techniques which we use when we are dealing with a solid sample. Now, this major analysis of the forensic samples, they take place in one of the mid IR windows. But what is happening in the near infrared and far infrared absorptions? The techniques and applications of NIR and FIR are quite different from those which we discuss with mid IR. NIR, they show some similarities to UV. Why? Because the spectrum region, when we say the electromagnetic spectra, CGX-UV IMR, the visible region is near to the near infrared region. So, indeed the spectrophotometers used in these regions are combined with UV visible to NIR ones. The majority of the absorption bands observed are due to overtones of fundamental bands that occur in the region 3 to 6 micrometer, usually, which are hydrogen stretching vibrations. So, if we are measuring the near IR regions, we go for the analysis of the hydrogen stretching vibrations. NIR is most widely used for quantitative organic functional group analysis. The NIR region has been used for the qualitative analysis and studies of hydrogen bonding, solute solvent interactions, organometallic compounds and inorganic compounds. So, that window particularly can help us in analysis of such compounds having inorganic bonds and organometallic compounds. Whereas, if we are talking about the far IR spectroscopy, they are carried out with FTIR spectrophotometers. The far IR region, they can provide very unique information. The fundamental vibrations of many organometallic and inorganic molecules, they fall in this region due to the heavy atoms and weak bonds in these molecules. So, the lattice vibrations of the crystalline materials, they occur in this region where we have electron valence conduction band, transitions in semiconductors which often correspond to the far IR wavelengths. So, as we said, the infrared spectra, it is based upon the transmittance versus the wave number. This is just a convention we are using. Now, if we look at the spectra of CCl4, this is carbon tetrachloride, we can see that there is one peak which is at the 770 centimeter inverse. So, coming and comparing it with the database, we can say if the peak will come at 770 centimeter inverse, then it belongs to the molecule CCl4. The vibrations of the molecule are in such a way that in the IR spectra, the wave number and the peak is coming particularly at the 770 centimeter inverse. Similarly, with the advent of various research techniques, we have seen where does the different kind of peaks will lie of the different molecules. And also, whenever we are buying an IR spectra, there is a whole database and library where we have peaks of various different chemicals and the bonds, and we can identify what is the composition of that particular molecule which we are analyzing under the IR spectrophotometry. So, this is a valuable forensic tool for identification of unknown substances, from drugs and explosives to paints, fibers, body fluids, and most importantly, this provides a molecular fingerprint which is essential for crime investigation and evidence analysis. So, this was the discussion about the dispersive spectrophotometers. Coming to the FTIR region, where we have the Fourier transform methods, which provides an alternative to the use of monochromators based on dispersion. So, what used to happen in the conventional spectroscopy? Frequencies are separated and only a small portion is detected at any particular instant. Wherever the remainder which is there, that is being discarded. So, the immediate result is a frequency domain spectrum. FTIR, when we say, it generates a time domain spectra as the immediately available data in which the intensity is obtained as a function of time. So, how that is being done? It is being done using a mathematical theorem which is Fourier transform theorem. So, whatever spectra we are getting, it generates a time domain spectra and we get the intensity as a function of time. So, which helps us, the FTIR spectra is a more efficient technique compared to the conventional dispersive IR spectrum techniques. The direct observation of a time domain spectra is not immediate. However, it is useful because it is not possible to deduce by inspection the frequency domain spectra from the corresponding time domain waveform, thus how the Fourier transform is being introduced. The major difference between the FTIR spectra and the normal dispersive spectroscopy is that the FTIR, they use interferometers. So, in interferometers, the major one type of interferometers which is used in FTIR is Michelson interferometer. What happens in an interferometer? We have a combination of a moving mirror and a fixed mirror. So, whenever the source is being passed, there is a beam splitter which divides the beam into two parts. The half of the beam goes to the moving mirror and half of the beam goes to the fixed mirror. So, whenever the radiation is coming back to the beam splitter, sometimes there is a constructive interferograms and sometimes there is a destructive interferogram. So, combination of that gives us an interferogram spectra, which further helps us in the analysis of the IR spectra produced by the FTIR spectroscopy. The Fourier transform spectrophotometers is basically the mathematical procedure which is employed to convert the IR interferogram, that is intensity versus time, also called time domain, to an IR spectrum. The intensity versus frequency, also called frequency domain, is called Fourier transformation. The heart of any FTIR spectrophotometer is an interferometer, and the Michelson interferometer consists basically of a beam splitter and two flat mirrors. So, in what happens in FTIR, as I said, there is a fixed mirror and an interferometer arm, and the other mirror is movable in the second interferometer arm. As we can see in the diagram, there is an IR source where we have sample compartment. On the top, we can see in the middle that there is an interferometer. This interferometer has a fixed mirror and a movable mirror, and then there is a mirror down also. This beam splitter which is coming from the IR radiation, the beams which are falling upon the sample, they are in the waveform which can be constructive or destructive. The laser source is being used in FTIR spectroscopy, and the radiations which are falling upon our sample, these radiations produce an interferogram. These interferogram are then further converted into the spectra. So, in one arm of the interferometer, IR source radiation travels through the beam splitter to the fixed mirror, back to the beam splitter, through the sample and the detector. In the other arm, the IR source radiation travels to the beam splitter, to the movable mirror, and back through the beam splitter to the sample and to the detector. The difference in path lengths of the two beams is the retardation, and helium laser is used as a monochromatic reference source, and the laser beam is sent through the interferometer in the opposite direction to that of the IR beam. This is an interferometer. This is one of the example of Michelson interferometer, where you can see one movable mirror is there. We have sample, we have detector, we have a fixed mirror. We have a beam splitting mirror through which the radiations are coming from the movable mirror as well as the fixed mirror. So, whenever a beam splitting mirror is there and the radiations are coming from the movable mirror and the fixed mirror, the beam splitter, depending upon the radiations, they are being passed through the sample. The sample, it takes the radiations as the constructive as the destructive radiations. The sample, whenever this is being passed through it, an interferogram is being prepared. The lower we can see is the interferogram, and this interferogram is being detected by the detector. The major difference between the dispersive spectrophotometers and the IR is that this interferogram which is being detected by the detector is converted to the spectra later on, and then we apply a Fourier transform theorem to that. So, if the moving mirror, it moves 1/4 lambda, waves are out of the phase at the beam splitting mirror, and then there is no signal. But if the moving mirror, it moves 1/2 lambda, waves are in phase at beam splitter mirror, and then we get the signal. That is how an interferometer works. So, the interferograms which are being produced by, depending upon whether there is a signal or there is no signal, we can get different cycles, and thus we can say this is in a time domain, and these interferograms are further converted into the spectra, where we are using the Fourier transformation theorem, which is a mathematical theorem. Now, compared to the dispersive spectrophotometers, there are certain advantages of FTIR over the dispersive spectrophotometers. They have a very high resolution, which is more than 0.1 centimeter inverse. So, what happens because of the two closely spaced line, which can be only separated if one complete beat is recorded. So, as line gets closer together, the delta must increase. So, delta V centimeter inverse is 1 by delta. When the mirror motion is there, we can even differentiate between two closely spaced lines. That means, if there are bonds having the almost same stretching frequency, that can also be resoluted using FTIR spectra, one of the major advantage compared to the dispersive spectrophotometers. They have very high sensitivity. In fact, the nanogram quantity of any material or any specimen which is present in our sample can be analyzed using the IR spectrophotometers. It can be coupled with GC analysis. We can measure IR spectra in gas phase. High SN ratio, what is SN ratio? Is signal to noise ratio, which is high throughput. That means few optics, no slits means high intensity of light. So, whatever signal we are sending, noise ratio is very less and the spectra which we are getting through the FTIR is a very high intensity of light. Very rapid it is, reproducible, and it is an inexpensive instrument. So, that is why we call the IR spectroscopy as a versatile technique which is being used in the forensic analysis. Whatever spectra we are getting through the FTIR, for routine instrument calibration, run the spectra of polystyrene film at the resolution of 2 cm inverse. Band positions we can see from the literature, and the high resolution calibrations may be made from gas phase spectra. So, whenever we are using the IR instrument, we have to calibrate the spectra also. Coming to the spectroscopy in the forensic science, the limit of detection using infrared spectroscopy is the presence of another is about 5%. So, comparatively, if the 5% of the sample is present in our specimen, that can be analyzed using the IR spectroscopy. Whereas, we say the IR spectroscopy is not a good technique for the detection of trace copolymers, residual solvents, low level pigments, nor it is of any use for the detection of manufacturing impurities or trace contaminants in illicit drugs. Although, when we say that the limit of detection can be a reliable qualitative tool, and even semi-quantitative analysis can also be performed using this. We use a set of calibration data comprising of various known mixtures, for example, heroin and sucrose. So, a relatively accurate quantitative analysis of unknown mixtures of heroin and sucrose can be performed, where we can see in the various chromatographic techniques that are somewhat independent of matrix identity, matrix contribution must be accounted for in quantitative infrared spectroscopy. For example, if we say we have to estimate the level of heroin drug in the glucose using calibration data obtained from mixtures of sucrose and heroin. So, specific calibration sets must be established for each types of analysis. It can also be used to elicit structural information which is difficult to or impossible to arrive at using other techniques. So, all the structural informations can be analyzed using the IR spectroscopy. Another example, if I provide you with that, there are distereoisomers, for example, ephedrine and pseudoephedrine. They are not distinguishable by mass spectroscopy, and depending upon the stationary phase used, they might exhibit identical rotations in a gas chromatograph. So, distereomers are stereoisomers that are non-mirror images of each other. So, these are not identified in fact using MS or GC, but IR is a very well versed technique where we can identify using the IR spectroscopy. Using the infrared spectral data, the bending vibration and the stretching vibrations in these molecules, they are very different, and through IR spectroscopy data we can differentiate between these two compounds which are easily distinguishable, and the IR spectra which is we are getting is different of these two compounds. So, certain compounds which are not identifiable using MS or GC can be identified using IR spectra. Also, we can say that the NH stretch in an amine salt is also found between 2500 and 3000 centimeter, whereas the NH stretch in its free base is found well above 3000 centimeter inverse. So, basically the bond is same, which is between N and H, but if it is present with certain other salt, it has different peak, and when it is found in free base, it has different peak. Thus, depending upon what kind of structure is there, what kind of bond is present there, we can identify different types of IR radiations using different spectroscopies. So, coming to the IR spectroscopy, we have attenuated total reflectance spectroscopy, which can be coupled it with. We have drifts, where we can couple it with another spectroscopy. The drifts, the positive part is that there is minimal sample preparation and we can put direct sample over it. So, to conclude, I will say that the IR spectrophotometers with array detectors can be considered a new class of IR instruments, and the size of an array detector chip with its sensitive elements placed in one plane can help us in the identification of various forensic specimens. Thus, combining FTIR with other techniques, we can have a conclusive result of the forensic specimens, which can help in the identification of compounds and further solving the criminal cases. Thank you.